All right, hello. Many faces I've seen before, that's good. Welcome to my talk. My talk is going to be about accelerating HDO and Envoy, or the overall service mesh space or technology that is evolving, using Cilium, using BPF, and using the Linux kernel. Why the Linux kernel? My background is kernel development. I've been a kernel developer for the last 15 years. I was at Red Hat for 10 years and helped develop the Linux kernel's many features. So I've worked on iptables, I've worked on NetFilter, on IPv6, IPv4, routing, Open vSwitch. So I've been helping construct a lot of these components that we're using today. And the next generation that is coming right now is BPF. So I want to talk a little bit more about BPF and give you a very specific examples how we can leverage BPF, percolate packet filter, to accelerate Envoy and HDO. So BPF, the superpowers of Linux. This is what Brandon Graf at Netflix called this. I'm going to dive into a couple of use cases where BPF shines. There are many use cases. These are the four that I'm picking for this talk. The first one we're looking into is how Facebook uses BPF and XDP. XDP is a special version of BPF to do load balancing. Load balancing at L3, L4, so not the service mesh use case at L7, but just L3, L4 load balancing and DDoS mitigation. We're looking at how Netflix and Brandon Graf uses BPF for profiling and tracing, finding the bottleneck in applications. We're looking at BPFD, which is a project by Google that allows tracing and visualizations on a large set of servers. So how do I trace, how do I get profiling data out of 1,000 servers that are running without having to log on into every server? And then the last one, why the heck is the Linux kernel community currently replacing the in-kernel part of iptables with BPF? So these are the four use cases we're looking into step by step. That kind of gives the foundation and gives an overview of what BPF can do. And then we're going to explain how that applies to service mesh. So Facebook published these numbers out of the blue about 2 years ago at the conference. Facebook is not very public about everything, so they're not actually publishing the absolute numbers, the absolute performance numbers, but they've published this slide. And what this slide is showing us is they have been using IPVS, which is a Linux-based, software-based load balancing technology that has been in the kernel for over 15 years. They've been using IPVS for many, many years. And then they've experienced the powers of BPF and how they can leverage BPF to get better, faster load balancers. And the performance difference with BPF was 10x, which was way too good to be true, so they've obviously repeated the measurements many, many times, just feeling like are we actually measuring correctly? But the numbers are, the reason for these numbers is because BPF is kind of changing the game. First of all, BPF features a JIT compiler. So BPF is capable of programming the kernel, but then the kernel will, on the fly, take software instructions and compile them into what the CPU understands. So it's almost like you would recompile the kernel on the fly and reboot it, but without actually rebooting it. So you can kind of modify the behavior of the kernel, and you can do this in a safe way. So amazing, isn't it, right? So and this power is being used for in this example for load balancing. So we've done something similar in Cilium, where we use BPF and XDP for DDoS mitigation. So this is a very simple example where we use a BPF program to drop connections from IP sources that are hostile to us. So the typical DDoS use case where you have a large pool of IP addressing spamming your servers and you want to drop these packets as quickly as possible. This demo shows, or this table shows, basically two machines. One machine is spamming the other machine with 11.6 million packets per second. Then we have the first setup, which is dropping all of these packets with a single iptables rule, running ipset, and just looking at the source IP and dropping all of the matches, right? And the second program is doing, or the second setup is doing the same with BPF. In the iptables ipset version, we can only drop about 7 million packets out of these total 11 million packets. This means that this server, this machine, is basically occupied 100% by just dropping packets. So this is just basically showing this is a successful DDoS attack. The machine is using all of its powers just to drop packets, which means that the latency has gone up and we can only handle about 280 requests per second of good traffic. In a BPF use case, first of all, we can drop all of the hostile packets. We can still, while this machine is under attack by 11.6 million packets per second, we can still process over 80,000 requests per second of good HTTP requests or good TCP requests. This is the second use case, which is profiling and tracing. Some call this the dtrace for Linux. Many have been waiting for this for many, many years. Dtrace has been super powerful, and Linux has always lagged behind a bit. So BPF gave this flexibility and the power and the visibility to bring something that's maybe not quite there yet, but very, very close already to dtrace. I'm not going to talk too much about this. If you are interested in this, go to Brandon Gregg's blog post. I have the URL on the slides. It has many, many examples. It gives instructions how you can generate these amazing flame graphs that can basically track down which parts of your applications are consuming CPU. Then Google came around and said, well, this is amazing, we want this, but we need this at scale. Right? We cannot really, like the previous examples, this BCC, this BPF compiler collection, has examples that allow you to run this on one machine. Google does everything at scale, so yes, they created BPFD, which gives you the ability to do the same, but for 1,000 servers, without having to manually do something on every server. Basically, it gives you the capability that if you're running an application at scale on many, many servers, you can profile them while they're all running at the same time, and you can figure out what each of them are doing on each server. Basically, expanding the profiling and tracing capability to a set of clusters or a cluster of machines. Then the last one is iptables. So what is your favorite memory of iptables? I think a lot of us have moments where we maybe we're in the middle of troubleshooting a huge iptable setup with many hundreds or even thousands of rules. Maybe several components, maybe a queue proxy, maybe something else, modifying this iptables rule all the time. Maybe an attempt to delete an iptables rule and another component re-edit this again. I think we all have memories in that regard. I like this quote. So Jerome has heard this. I don't think he mentioned this himself, but in any team, you need a tank, you need a healer, you need a damage dealer, someone with crowd control abilities, and another who knows iptables. And I think that's very true. So what's happening right now, and this is not making iptables obsolete per se, but the kernel community has basically decided the future is BPF. We don't want to maintain both a BPF-specific data path and then also maintain this upcoming next generation of networking featured by BPF. Can we somehow translate iptables, like the configuration requests by the user, and use BPF to implement this? And this is what's happening now. It's called the BPF filter project. It basically allows you to continue using iptables, but the kernel itself will use BPF to enforce this. And just by replacing the enforcement part, we're already seeing massive performance increase. So this graph is an early benchmark that shows in yellow existing iptables performance, blue nftables enforcement, which was supposed to be the successor for iptables. Has been trying to do so for 10 years, but it's never really taken off. And then BPF filter, which is about 3 times or more than 3 times faster. So the gray is the softer version of BPF, and because BPF is a generic bytecode language like Java, it can actually be offloaded onto SmartNICs. So the blue one is BPF, but offloaded to SmartNICs. So this next generation of Linux networking is actually so generic and programmable that it can be offloaded onto SmartNICs for the next wave of performance needs. Excellent. And there will be many more examples. I have compiled a list here. We don't have time to go through all of them, but the amount of BPF-based projects in the last couple of months has basically exploded. So BPF is now everywhere. So what is this BPF? How can I use it? So a typical BPF chain looks something like this. So you have a user, for example, a developer, writes a BPF program in source code. This can be sudo C, it can be Python. And then there's a compiler right now there's two major ones. There's LLVM Clang, which can take pseudo C code, and there's BCC, which can take Python code, and both will then generate BPF bytecode. BPF bytecode is basically something that looks very similar to x86 assembly, but it's completely in software. This program is basically a computer program. You can then load this into the kernel and attach it to multiple points. You can attach it to whenever a network packet is being received, whenever a system call is being performed, whenever a trace point in the kernel is being hit, whenever a user space probe, so whenever a function in your application is being hit. So for all of these events, we can run a BPF program. So for the networking part, so for the, we're obviously using the packet hooks. For the tracing parts, we're using system call hooks, we're using trace points. For security, for example, seccomp, we are attaching this to system calls. So every system call being called, a BPF program runs and decides whether the caller is allowed to call to make this system call or not. So BPF basically gives us the flexibility to run these small little programs everywhere inside the kernel and extend the logic of the kernel itself. So I talked about BPF being safe. So how does that work? So when you load the program into the kernel, it goes through the verifier. And the verifier will look at the program and will make sure that it cannot hurt the kernel. Right? So it cannot crash the kernel. It has to be able to run to completion. It cannot loop forever. It cannot expose kernel memory. Right? This is the major difference between BPF and the Linux kernel module. Like if a Linux kernel module has a bug, if it has a null pointer dereference, it will crash your kernel and your machine will be dead. If the BPF program, you can load a faulty program, but the kernel will reject it and not load it properly. So only safe programs are loadable. And the last aspect is the JIT compiler. So this takes the software-only instructions and compiles this to x86, ARM, and so on. So basically, instead of having a software-based virtual machine that runs the program, it gets translated into something that the CPU understands, so it runs at native speed. This is why we get this amazing performance. So how does BPF, how does all of this apply to Envoy and service mesh? So I think all of you have heard about service mesh, Istio, Envoy this week, so I'm not going to do an intro on that. If you don't know about it, there are many good talks that have been recorded this week, so I recommend watching one of those. But overall, it looks something like this, where we have two services, and they use a sidecar on each side to communicate with each other. So instead of services talking through the network directly, we basically inject a sidecar proxy inside of each pod, which then talks on behalf of the service. This allows, for example, to do retries. So if the service at the other end responds with a 5x HTTP, we can, for example, retry and do this again, right? It allows to do tracing and so on. You all know about the promise and the values that a service mesh can provide. And if you look at this picture, it looks pretty simple. It looks neat. It's a good architecture. If you now look at what's actually going on under the hood, you might see where some of the performance overhead is coming from. And this has nothing to do with the proxies themselves. It's all outside of the proxy. It's how the proxy is being put into the picture. So first of all, what do all applications use to talk to each other? They use sockets, right? So the service, the application, opens a socket and makes an outgoing HTTP request. The sidecar itself, the proxy, listens on a port. It's also a socket. I then will open a second connection on behalf of the application. That's another socket. And then this same picture is on the receiving side. So we already went from 2 sockets to 6 sockets. Because if the services would be talking to each other, obviously we'd also have sockets, but only 2 of them. Then what do these sockets talk? They talk TCP. So we're going through the TCP stack. The kernel itself is not able to do forward L3 only, which means that it cannot actually forward TCP only. It needs a layer 2 protocol as well, and basically we're still talking Ethernet here. So yes, let's add Ethernet to the mix. So it's maybe a bit surprising that an application is talking to a sidecar and Ethernet is involved. But even that, so Linux does everything with files and devices. So where are my devices? Let's add the devices to the mix. So from app to sidecar, this could be the loopback. Right? This is the case where you tell the sidecar, where you tell your application to talk to the sidecar directly. So let's say the sidecar is listening on port 4000. You're telling the application, instead of talking anywhere, talk to 127.0.0.1.4000, talk directly to the sidecar. This is this model. Even in this model, we're already going through the TCP stack 6 times. We're going through the Ethernet stack 6 times. We're going through 4 different devices. All of this adds a lot of latency. It's literally running through millions lines of C code inside of the Linux kernel. If you want to do this transparently, so without having to tell the application to talk to the sidecar, we have to add something else. And this is an iptables rule. So if, for example, if you deploy Istio right now off the box, you get an iptables redirect rule that's running inside of the pod that will redirect all traffic that wants to exit the container, that wants to exit the pod, and redirects that back into the sidecar. This is this iptables rule. We're not going through this rule once, we're actually going through this rule twice, because when the sidecar then opens the second part of the actual real connection that goes out, that also goes through that iptables rule. That rule will actually have an exception and says, well, if you are coming from the sidecar, then I'm not redirecting you. Everything else gets redirected to the sidecar. So we're actually hitting this cost twice. And then obviously on the incoming side as well, any packet, any connection that goes into a sidecar or into a pod gets transparently redirected to the sidecar. This is all, like the sidecar is always in the same pod, or is always running next to the application. It's always on the same node. Why do we use Ethernet? Why do we use TCP? TCP has been designed to survive nuclear blasts, right? So TCP has been designed to survive lossy environments where packets can get lost. If you're staying on the same node, packets are not getting lost. In fact, it's basically just data. It's data that we have to move from the app to the sidecar. Why do we use TCP and Ethernet? Yeah, so why do we use it? I don't really know, because it's possible to do it without it. And this is where BPF and Cilium comes in. So in this case, where you run the sidecar model, for example, with Envoy, we notice that both the application and the sidecar are on the same node. And we're just taking TCP, Ethernet, and all of this out of the picture. Right? We have 2 local sockets, and basically one socket is trying to send data. It doesn't need to be TCP, and the only intent we have is move that data to the other socket. So why don't we just move it over? And that's what we do with BPF. Right? This is the socket level BPF that we have added to the Linux kernel that allows you to do this. It obviously simplifies or it enhances the performance a lot, because we're no longer having to go through the TCP stack and so on. And the beauty of this is it does not require any changes at all, because the application is still talking TCP. The sidecar is still listening as a TCP socket, so nothing has to change. Right? You can run this as is. You bring Cilium into the picture, and it will accelerate this transparently for you. So what does that bring us? So we have done measurements, and kind of at the same moment, we were in the same moment as Facebook. Like, we have to measure this again. This cannot be true. Like, let's remeasure. We cannot just publish these numbers. It's too good to be true. So we've measured three cases. Blue is the iptables redirect. That's basically when you deploy Istio out of the box. This is what you would get right now. Orange is the case where you point the app to the sidecar, so you don't need the iptables redirect rule. So the difference between blue and orange is already that single iptable, the cost of a single iptables redirect. It's quite massive already. And then the yellow is Cilium accelerating this transparently. And it's somewhere between 3 to 4x faster. If you're wondering what the X bar here is, so the Y or the Y-axis is the number of requests per second. The X-axis is the number of persistent connections. Typically, if you're running service mesh or you're running with a sidecar, the app does not open a new connection for every request. Like most networking libraries will maintain connection pools and will reuse the same TCP connection multiple times for new requests. So the X-axis is the number of persistent connections that we're using in parallel. So yes, in this measurement, we found out that we need about 50 parallel persistent connections to actually max out the machine. And this is just a fact that your systems has multiple cores, so in order to maximize use of the machine, we have to do things in parallel. So how do we do this specifically? Or like what are the, if you look under the hood, what we found out, we wanted to make as minimal changes as possible. First of all, we did not want to emulate TCP or anything like that. So what we decided to do is we will keep the existing behavior for the handshake. So for the SYN, for the TCP handshake, so for the non-networking people, this is basically the initial 3 packets that are exchanged between sender and receiver to basically confirm, to build up a connection. These are 3 packets that are being sent initially, and after this, a TCP connection is established. So this still goes through the existing path. This is basically just a connection building up. But if you're using persistent connections, we're paying this cost once. And after that, we don't pay it anymore. And then only in the data phase, where we actually exchange data in both directions, do we use the acceleration. This means all TCP options, all flags, all of this just continues working. It's completely transparent. It's only the data that gets accelerated. We're even working on making it possible that you can still use, for example, TCP timestamps. This still works, but the data is still getting accelerated. This means there's no changes to the application required, right? If your application is using TCP sockets, you can transparently redirect to a sidecar to, for example, Envoy. Envoy does also not need any changes. It will simply benefit from this acceleration. But wait, this is actually not sidecar specific at all. This will work across any connection that connects 2 local applications. So it could be 2 containers talking on the same node. The sidecar is it's a perfect example because in this scenario, you always have 2 containers or 2 applications talking to each other. But it will actually work as well if you have 2 containers talking to each other, you're running Cilium, they will just get this boost automatically. So this also works across container namespaces. Right? The kernel itself is not isolated in that sense. It actually sees all the sockets. We will still respect namespace isolation from a security perspective, but if they are allowed to talk, we will accelerate this. So you will actually benefit from this, not even in the sidecar case, but also in just a plain forwarding case where 2 local applications or 2 local containers are talking to each other. So how do I get this? You can run Cilium, right? This is the way to get this. Cilium brings BPF to Kubernetes and other orchestration systems. I will talk a little bit about BPF or about Cilium and its scope in the next slide. But the main requirements to get this is for Cilium itself, you need to run a Linux kernel that is at least 4.9. Most distributions, for example, if you're running Ubuntu 18.04, you get this out of the box. CoreOS, you get this out of the box. For older distributions, let's say Ubuntu 16.04, there are kernels, so there's official packages, so you may need to reboot once to just run a more recent kernel than the default one. For example, Google announced or told us this week that the container-optimized Linux image that they're using for GKE is now also enabled to run this and so on. So most distros will bring you this. If you want to use the sidecar acceleration, that's a more recent feature. That is in 4.16. Right. So as you can see on this slide, Cilium is basically taking orchestration, or is combining or is translating orchestration system concepts like a policy, networking, load balancing, and translates that into BPF programs that get attached to containers, to pods. So it's basically doing the magic, so you don't have to know about and you don't need to know how to write BPF programs. We are doing this for you, but basically implement the known standardized orchestration system standards, like for example CNI or network policy or Kubernetes services and so on. So what exactly does Cilium? And I've tried to compress this into one slide, Cilium in a nutshell. So we have a release we released 1.0 a couple of weeks back. We're now at 1.01. We have this highly efficient BPF-based data path. It's fully distributed, so there's no centralized control plane anyway. Like all the functionality runs on each node, so it scales out really well. We have this service mesh data path, which is what I just talked about, this acceleration of the sidecar. We have a CNI and a CMM, that's the Docker libnetwork model. So we support these two models. CNI gives us Kubernetes, of course, gives us the more recent versions of Cloud Foundry, gives us Mesos, and so on. We implement network security, and we do this both at packet level. So this is the existing traditional layer 3, layer 4. This pod can talk to this pod on port 80. This is kind of the packet-based. We also have the API level, so kind of the world of API calls that Istio and service mesh cares about. So not saying that, yes, two pods can talk to each other, but they can only do certain API calls. For example, only a get to /public, but a get to /private should be denied. So I can restrict access to my APIs and shrink the API service. We can do this for HTTP, we can do this for gRPC, Kafka, and then more and more are coming. We're having very interesting conversation with Matt how we can simplify and lower the barrier to add more and more protocols into Envoy. On the security side, we can do traditional IP CIDR-based enforcement. That means you can say, I want to talk to this IP or this block of IPs. All cluster internal security is label-based, like all other plugins as well. So it's implementing the Kubernetes network security. The main difference is that we're using identity-based enforcement. So we're not basically mapping labels to IPs and then whitelisting individual IPs. We're actually generating a strong identity, and when a pod sends out packets, we're attaching the identity to the packet, and then we're verifying this identity instead of relying on source IP addresses. So similar to mutual TLS, I think this next wave of security has to be cannot be IP-based, it has to be identity-based. Then we do distributed and scalable load balancing on L3, L4. So basically complementing a service mesh, which would do this primarily at L7. They can also do L4, of course. We're doing this in a very efficient way. So we're replacing the iptables and IPVS version of proxy. We're doing this in BPF in a way that actually scales to thousands and thousands of services. The performance is the same whether you're running one service, 1,000, 10,000, or 500,000 services. It's a very efficient hash table-based lookup. We have a very simplified networking model, so we're trying to keep networking as simple as possible. We support an overlay mode, which is kind of VXLAN Geneve based. We also support a direct routing mode where you can run your routing daemons. We're trying to not actually restrict you to one specific routing daemon, so you could run something like a kube router, you could run Zebra, whatever. This will function, and then in one of the next releases we'll have delegation to another networking plugin, which means that maybe you're already running Flannel and you don't want to change this, but you still want to have the benefits of, for example, the service mesh acceleration. You want the scalable load balancing with Cilium. You can run Cilium on top of other networking plugins. And then we have visibility and tracing. This is basically bringing the power of BPF in terms of profiling and tracing and bringing that as well. So that is definitely the least advanced feature that what we have right now, but this will be the focus in forthcoming releases. But wait, it actually gets better. The exciting part is coming now. And it's a little bit scary, maybe. Let's see. So TLS usage in service mesh, very simple. Sidecar is running on both sides, right? The sidecars are implementing the actual encryption. Service to sidecar is unencrypted. The sidecar can see HTTP requests, can, for example, do path-based routing, can do hostname-based routing, and so on. Simple. We all understand this. How does this look like if we're talking to external services? Let's say a GitHub API or a payment service API, something that's outside of the cluster. In that case, the application is obviously using TLS encryption, and it's encrypted in the application itself, right? The application is using SSL to talk to GitHub using HTTPS. You're definitely not going to send your password clear text across the internet, right? So how does that work with a sidecar? Because at this point, the HTTP payload is already encrypted. How do we solve this? I think there are two options. The first option is we could actually inject a root CA that basically allows the sidecar to decrypt. So the sidecar will basically behave as if it was github.com as an API. I've heard this a couple of times this week. There are people that are thinking about this, because this is kind of, if you don't know about the next step that I'm about to explain, this is kind of the obvious hack that we could put in place. I'm seeing like heads, no, yeah. No, it's not what we want. So that's actually a beautiful solution that we can provide in the future, which is KTLS, which stands for kernel TLS. So KTLS is actually not that complicated. What it does is the kernel already has a very rich set of ciphers for crypto, for IPsec. So it can already do encryption. So what KTLS does is it keeps all the complicated logic of negotiation, keys, and all the control plane, all the handshake, all of that remains in the SSL library. But then once the key is known, the key is pushed down to the kernel, and the kernel will do the symmetric encryption part, the actual encryption of the data. This was not added because of of this use case. It was actually added because a lot of static content providers, they saw a 3–4% CPU reduction of this method. If you are streaming video data over SSL, 3–4% CPU reduction really matters, right? You just need less machines. So basically, the encryption point moves from the SSL library to the socket layer inside of the kernel. Let's combine this. So this brings the previous picture back, which is kind of application, socket, sidecar. What if we actually delay this further and do the encryption after the sidecar? So we have the key, and at this point we know it's going into the sidecar. What if we don't encrypt there, but only encrypt after it went through the sidecar? In this case, the picture will look something like this. Even though we are talking to an external service, we're not changing the root CA in any way. The sidecar or the app-to-sidecar communication will be unencrypted. The sidecar can see the plain text HTTP header, can do routing and so on. But when it leaves the sidecar, it gets encrypted with the key that was negotiated by the application in OpenSSL or in whatever SSL library you are using. That solves the problem, right? And the kernel is a trusted entity and does this for us. We can trust the kernel to do this. It's delaying, it's making the sidecar part of the application that's using SSL, right? So it solves this, and it does not even require us to decrypt. Like even in option 1, if we go back, even if we would want to do this, you would have to decrypt at that sidecar and then re-encrypt again, which is obviously a massive latency and CPU overhead that you're adding. So what do I need to get KTLS? In order to get KTLS, it was merged a couple of weeks ago. So it was a joint collaboration between us, Facebook, and Google, and some others. You will need a recent kernel, and you will need an OpenSSL or an SSL library that knows about KTLS, which also means you actually need to opt into this. So if you don't want this, you can basically say, I don't want to grant the kernel this capability. You need to opt into this, right? Which means that the kernel cannot just magically see into your data if the application encrypts it. The application must allow this deferred operation of the encryption. I think right now the support is baked into GNU TLS and OpenSSL, and I know that support is coming for the for the Go version of the SSL library, and also for boring SSL. So basically, this gives us like sidecar for TLS encrypted connections without CA injection, without decryption. When we basically thought about this, I had this wow moment, like kind of this will change a lot of things, because in the end, it's like things are always simple if you control both sides, but a lot of communication, it will be to external services. So how do we, for example, do retries to an external service? How do we do retries to a GitHub API without actually baking this into the application? And I think this will basically open up sidecar functionality to the world of external API calls or the world of external services. Excellent. What day is today? So today is May 4th, so may the 4th be with you. So we have a little present because we're actually very, very, very close to 2,000 stars. Let me pull it up. I want to do a quick, let me refresh it. So what we'll do is the following. I have the following little present here, which is, we're in Denmark. So this is Lego, this is a Star Wars Lego spaceship. And if you are storing the Cilium repo in the next 10 minutes, let's say left 5 minutes, the next 5 minutes, we will pick a random star person and we'll give away this Lego box. So before you start, stop. Don't start yet. I have to refresh first. We'll look at who started last, and then we'll count the number of stars. All right. All right. So Alexandra is the latest person that I'm really sorry if you're in the room, but you don't have a chance to win it. So if you star in the next 5 minutes, we'll count the number of new stars and we'll give away this Lego box. And with that said, I'm opening up for questions. If you have questions, please come to the microphone and ask them. We have, I think, 5 minutes for questions.
Hey, I have a question about iptables. So my understanding is like one of the downsides of iptables is that under the hood, every time you change a rule, you actually have to unload and then reload the entire rule set.
Yep.
Can BPF do, say, like partial recompilation, or like does it suffer from that same downside?
iptables has this problem. You can only replace an entire table, which means entire chains, right? So the entire filter table. And for example, nftables already doesn't have this problem anymore. BPF also doesn't have this problem. Like in BPF, you would compile the program, load it in, and then use BPF maps, which kind of contains the state, for example, the policy. And these maps can be updated like multiple 100,000 of times per second. It's kind of incremental updates. So BPF does not suffer from this problem in general.
Thanks.
But that said, the BPF filter project, which is kind of this iptables compatible version, does not solve this problem because it's an iptables fundamental problem. So BPF only accelerates the actual enforcement of it. Yes.
Yeah, just a quick question. So I've been reading on LWN recently about XDP sockets, like AFXDP.
Yeah.
So I'm curious how that fits into all of this.
Awesome, yeah. So XDP is the BPF version that runs at the network device driver level. It actually allows BPF programs to look into what's in the packet data on the DMA buffer, like very, very close. This is what we use for DDoS protection. AFXDP is a way to export this data to user space. So this, for example, allows us to build a very fast, very efficient new version of TCP dump, for example. That is super low overhead. It allows us, for example, to gain insight into what is going on at the network device layer without actually copying data around. Cilium currently does not use this, but we definitely have plans to use this. It was only merged a couple of weeks ago.
Thank you.
Okay, if I use the normal TCP stack, also for the application to Sidecar communication, I can use TCP dump to debug.
Yes.
If we redirect with the sockets, is it possible with TCP dump also to debug?
So you will see the handshake. You will not see the data.
Okay.
But we expose information via a BPF specific way. If we would do this, if we would actually expose this through TCP dump again, we would lose all of the benefits we've just gained. But you will still see the connection opening, and you will still see the connection closing, but you will not see an entry for every single data packet because there's no packet. Right?
Okay.
It's just,
can I see this with Cilium?
yes, correct. Yes,
okay.
You can.
Thank
So even for the non-sidecar case, you can still use TCP dump if you want. We have a more efficient version of TCP dump that also gives you more context. So instead of just IP addresses, we'll, for example, show you, hey, there is a container with these labels talking to this container with these labels, instead of just this IP to actually this IP. So we have a microservices-ready TCP dump clone. All right.
So you talked about Cilium working with Envoy and you know all the performance gain that we are getting. But I think in Austin we did come to you and we asked about is there a possibility with Cilium not working without Envoy?
Oh yes, so Cilium uses Envoy for all layer 7 enforcement. So whenever you have a policy rule that requires to restrict on HTTP level, Cilium will automatically get Envoy into the picture. If you don't have these rules, then we will only go through Envoy if we need to, right?
So the question, so the main thing was, the main concern, we did not wanted to introduce Istio. This was last year, and well, the reason we could not go for Cilium at that time was because Cilium was too intertwined with Istio. Is that still the case?
So we have just finished a prototype where we run side by side Istio, where basically Istio pilot manages the Envoy instance for all the pods, and Cilium talks to that same Envoy instance. So basically, instead of running 2 instances of Envoy, we basically use the same instance. So it's now tightly coupled. Actually, I think we are running out of time, and I want to make sure that I give this away. So let's see, we were at 1968. So let's see. All right, we made 2,000 stars. All right. So let's see. I need Google for the math. So we have 68, 32. So pick a number. So we have received 74 stars. We'll have Google pick a random number for us. So the number is 7. So we go back to the stars. We reload this, and we'll go to Alexander and then count 7 up. All right, so 1, 2, 3, 4, 5, 6, 7. Simon, where is Simon? All right, here you go. Thanks a lot for your star. Yeah. All right, so I think we have a couple of T-shirts left in the back. Unfortunately, we ran out of some sizes, so if you still want a Cilium shirt, we also have stickers. Make sure you check at the exit. I'm also available outside for more questions.